in the hopes that we can get through what we need to get through here today. So where we left off was right at this extra example, and this is below the half angle identities. So it just says extra example right after the half angle identities. And where we stopped was the cosine of 7 pi over 8. Didn't quite have enough time for that. So when you look at that angle, you should be thinking, well, there's nothing special about that. But you realize, hey, wait a minute, if I take 7 pi over 4 and I cut that in half, I've got 7 pi over 8. So this is perfect for our half angle identity. 7 pi over 4 divided in half would give us that. And so what we do is we try to figure out, what quadrant is this going to be in so that we'll know whether or not it should be positive or negative. Well, the good news is we actually know what the angle is. It's 7 pi over 8. So it's going to be in quadrant 2, and they want cosine. And in quadrant 2, cosine is negative. So we're going to be using the negative formula for, and maybe so I can see it without my glasses, for the half angle identities. So we're going to use a negative square root of 1 plus the cosine of 7 pi over 4. We're going to use that in the formula. And that's going to be over 2. So it will be negative square root of 1 plus, now we figure out what is the cosine of 7 pi over 4. Well, 7 pi over 4 is 1 3/4 pi. But this certainly reminds us, hey, that's going to be pi over 4 there, and this is a 45, 45, 90. So we've got 1, negative 1 as the coordinates on that terminal side, and then the square root of 2 for our hypotenuse. And maybe you've already got your square root of 2 over 2 done. But if you didn't, you could always use the drawing, and you could say cosine will be adjacent over hypotenuse. That's 1 over the square root of 2. Oh, wait a minute, that's going to be square root of 2 over 2. Divided by 2. And since we made the drawing, we don't have to worry about the positive and negatives, but cosine is in the 4th quadrant, which is positive anyway. So now, what do we do with that? Well, we make it look a little nicer, So what we had to do here is figure out, well, can I get this stuff together? Can I make this look nicer? And we're dividing by 2. We might want to go ahead and say, let's make this one fraction, and then we have that 1/2 to deal with later. So 1 would be 2 over 2, so that'll be 2 plus the square root of 2 over 2. And then we say, okay, well, if I'm dividing by 2, I'm going to multiply that by 1/2 on the top and the bottom. So really all it does is make my 2 that's on the bottom into a 4. And we would want to separate that. So we're not going to have a radical in the denominator. That's going to work out really nicely to a 2. That's a perfectly fine answer. Like I said, you'll have some professors at college that will say, instead of leaving that 2 down there as a fraction, just put negative 1/2 in the front. But I'm going to take it either way. They're both exactly the same answer. It's just a matter of how people want to write it. So the quadrant is important so we can know whether or not it should be positive or negative. And then after that, we just use the formula and use what we know about these angles in advance. That's the whole reason we're doing this. We want to get some perfect answers. But what we see here is we had ourselves a nice embedded radical, a radical inside a radical. And this next example really forces us to think, okay, what do we do with that if we have to get rid of it? How do you get rid of a radical inside a radical? So this one says we're going to find the tangent of x over 2 if the sine of x is negative 2/5, and x has to be between pi and 3 pi over 2. Well, If x has to be between pi and 3 pi over 2, that puts us in the third quadrant. And it said the sine of x is negative 2/5. So if I draw my little reference here, put my little x there, that means that opposite over hypotenuse is negative 2/5. And it makes sense that we'd have the negative 2 and our y coordinate there since we're going down. But the first thing I would want to know is, well, what's the other one? We're probably going to need that as we do this problem. So negative 2 squared plus something squared. I hate to use x again. Maybe I better change that to like y, even though it's the x coordinate there. And we realize, well, we've got 25 minus 4. That's going to be 21. So this is going to equal the square root of 21, but it's a negative square root of 21 because we're going to the left. All right, we got a great start, and we have that it has to be between pi and 3 pi over 2. But the answer is going to be half that. I start thinking, right now, my angle x is between these two. And what I'm going to have to do is divide that in half, because I've got x over 2. Well, that means multiplying everything that we have here by a half, so we'll know which quadrant we're in when we're done, what our answer should have for a positive or negative. So pi over 2 is less than pi over 2, which is less than or equal to 3 pi over 4. Which quadrant is our answer? Oh, thank you. Made another pi there. There we go. So which quadrant? Quadrant 2, and we're supposed to find tangent. Tangent is negative in quadrant 2, so our answer is going to need to be negative. So now it's a matter of, we've got 3 different formulas that we're supposed to use for tangent of x over 2.
So why is it lesser 3 pi over 4?
Well, I could just put, actually we could put either one there if it were quadrantal, but I'll go ahead and take my equal graph there so we stay consistent. Because it wouldn't matter, but let's just be consistent. So what we're going to do is we're going to use the first formula. And we'll see how that first formula works out. So we want the tangent of x over 2, and we said that already we realize that's going to be negative. So we're not going to do the plus or minus thing in front of there. And 1 minus cosine of x. Over 1 plus cosine of x. Well, that's not so bad. I mean, we've got a drawing and everything up there. This can't be that awful. Let's see. Negative square root of 1 minus cosine of x. Adjacent over hypotenuse. So negative square root of 21 over 5. We're going to have to use that twice. All right. So first things first. We've got some sign issues here. Let's take care of that. So this will be a negative square root of 1 plus the square root of 21 over 5. But while I'm at it, you know, it looks like we're going to have a fraction on top and a fraction on the bottom. Maybe I better get a common denominator and multiply this one by 5 on the top and the bottom. Kind of do 2 things at once. So that would give me 5 plus the square root of 21 over. And on the bottom, same thing. But now we have plus a negative, so that's really going to be subtraction. So we can see there's 1 fraction over 1 fraction. Well, that's a little helpful. I mean, what we need to do is multiply by the reciprocal. So we can get just one fraction underneath there, so that'll be negative square root of 5 plus the square root of 21 over 5 times 5 over 5 minus the square root of 21. Oh, good! One set of 5's cancel. So we'll have negative square root of 5 plus the square root of 21 over 5 minus the square root of 21. Bravo. We're supposed to rationalize the denominator for these, because these are supposed to be perfect. Oh, okay. So how does one get rid of, because really if we separate these out, this is going to be negative square root of 5 plus the square root of 21 over negative square root of 5 minus the square root of 21. How do we get rid of that mess? Let's just think basic radicals, all right? These are square roots. We've worked with square roots before. So if we had this as a problem, 1 over the square root of 3, how did we get rid of the square root of 3? How do we get the radical out of the denominator? Multiply by the exact same thing as what we have on the denominator, right? Because then what happens is this. And we see inverses. We have a square root and a square, and they drop out. Well, that's got to be our first step here, because we've got 2 radicals inside there. So we first have to figure out how to get rid of this monster radical on the outside. So we're going to multiply by the square root of 5 minus the square root of 21 on the top and the bottom. I guess that gives us some good news in the denominator. One of the radicals is gone, because we'll have the square root of something squared. So we have 5 minus the square root of 21, and that's something we know how to deal with. But it's like, what on earth do you do up there in the numerator? Well, they're both radicals. You can multiply square roots times other square roots. We just need to do a little FOIL inside that obnoxious thing and see what we get. So we'd have our square root times a square root, which gives us a square root. In fact, I'll take my grouping symbol out there so that we don't have so many symbols that everything's getting lost. 5 times 5 is 25. Ooh, something good happened. Since we have opposite signs, that has that sum and difference pattern to it, which means outside times outside and inside times inside are going to cancel out. Thank goodness. Square root of 21 times the square root of 21. Wait a minute. That's 21. And 25 minus 21 is 4. And we know the square root of 4. Whew. We're getting there. We're getting there. Now the problem, and I'm trying to squish this in. I should have just moved my stuff down because that doesn't look like subtraction anymore. Now the problem is we still have a radical in the denominator, but at least it's only 1. So the first step to get rid of these square roots over the entire fraction is just multiply by exactly what you have in the denominator, and that'll get rid of them. So now we're here. And now, this is stuff you did in Algebra 2, where you know you're going to multiply by the conjugate to get rid of that last square root. So this will be 5 plus the square root of 21 on the top. And the bottom. And that would give us a negative 10 minus 2 square roots of 21 on the bottom. First times first is 25. We have a negative and a positive. Outside times outside, inside times inside. Cancel out. And down there, we're going to get a 4. And we realize all of the integers that we see are divisible by 2. So we can go ahead and make it a little bit better. And depending on the professor you have, they might ask you to write it that way, or that negative 1/2 out of both pieces. So now, look at the formulas that we have there for tangent of u over 2. Do you suppose that first formula was a good choice? We had to do at least one with it, but that is the toughest formula out of those 3. It really is, because it gives you the embedded radicals. So if you had a choice, you probably should go after 1 minus cosine u over sine u, or sine u over 1 plus cosine u when you do those problems. But this will work. It's just a lot more work because of the embedded radicals. And I needed to show you how to get rid of embedded radicals. So, questions on that one? All right. Now we're going to solve some stuff algebraically. Cool. So we're going to solve trigonometric equations using a double angle identity. We're first going to start by talking about the algebraic solutions just from 0 to 2 pi, and then we'll start going a little broader there. So we have the sine of 2x equals cosine x. And I realize to solve algebraically means we need to find the zeros, because that's what you're doing when you solve algebraically. So I'm going to need to move one of these over. It just seems logical that I would subtract cosine x from both sides. And usually it involves factoring. But as that one sits right now, there's nothing I can really do with it factoring-wise. So I grab my handy-dandy sheet and I say to myself, self, is there something helpful I could put in there for sine of 2x? Oh, look at that very first one in the double angle identities. It says this equals 2 sine of x cosine of x. Okay, that might be helpful. Well, sure it is, because now I can factor out a cosine x, because there's cosine x in both of those. This is the double angle.
She didn't have a sheet.
Oh, leave that. The green sheet is very helpful. We are not memorizing these. We are grabbing the sheet whenever we have to do these right here. Is there anybody else that was gone and didn't get a green sheet? Thank you for saying something, Emma. All right, let's pull the cosine x out of there. Well, that looks like problems we've done in the past. Because the zero product property says, well, either this is going to be 0 or this is going to be 0. And you can solve those and find them, because this was just from 0 to 2 pi. So cosine x equals 0. Think unit circle. Got the unit circle sitting in front of you. Cosine is always the x coordinate. So where is cosine 0 on the unit circle? Pi over 2 and 3 pi over 2. Straight up and down, right? 0 up, 0 down. Let me give the visual to those of you that are stuck right now. Remember, any point on here is cosine x sine x. Well, that one wasn't so hard. Let's try this one. Let's see, if we add 1 and divide by 2, Sine of x equals 1/2. So sine is opposite, so that means the opposite side would be a 1. That makes that a 30-degree angle, because the 1 is always opposite the 30-degree angle. So we think in 30 degrees, but we quickly change that over to what? Pi over 6. And in first quadrant, do we get a positive sign value? Which other quadrant gives us a positive sign value? Quadrant 2. So we need that reference of pi over 6 in quadrant 2. What would that be? 5 pi over 6. Good. Good. Now they just asked between 0 and 2 pi. So there they are. Those are all the solutions that this is going to work for from 0 to 2 pi. And we move on. Go to the next problem. Unless anybody has a question about that. No.
How do you from 2 sine x cosine x minus cosine x to stuff like that?
To this piece?
Yeah.
Now that we know we're going to have to factor because it says solve algebraically, I am looking for something that's common to both pieces. And pieces, the terms actually are separated by pluses and minuses. So I'm looking at this in the black and I'm looking at this in the red, and I'm trying to find something that's common to both of them. And cosine x was common to both of them. So I just factored that out exactly and got this. And that's going to be the process we're going to try to use for as many of these as we possibly can. All right, this one. Sine squared x equals 2 sine squared x over 2. Oh my. Well, we know we're supposed to do some factoring stuff, so maybe we better figure out what we could put in for that half angle piece there, huh? Let's see. So this is sine squared x equals 2. Now remember, this says sine squared x over 2, but it really means the whole thing squared. So we put our little plus or minus formula in here. Like so. And good stuff happens. First off, square root's gone, but so is the plus or minus because we're squaring it. So it's going to be positive. So this will be sine squared x equals, and we'll have a little 2 right here for just a second. Until we realize, well, the 2's going to cancel out. Gotta move everything over to one side and then think of a way to get something that would be factorable. Think of something we could put in for sine squared x that would have to do with cosine x. 1 minus cosine squared x. Exactly. So you go back to that basic Pythagorean identity. Now let's see. Well, we got a 1 minus 1, so the 1's are gone. We get a cosine squared x plus cosine x equals 0. In algebra, we learned we don't like a negative in front, so we could pull that negative out in front. But there's more we could pull out, right? Let's take a cosine out there. Let's do it. I want my parentheses to look like the C's. So far, so good? Oh, I had already pulled the negative out before. We just did that in 2 steps instead of 1. You could just pull a negative cosine out right here if you wanted to and reverse that. Or,
how did you get rid of the square root?
oh, remember, this is the part that we always have trouble with. This really means, I know, it's because of the way that we write it in trig, it really means that.
I didn't see you had the 2 up there.
Oh,
I was
okay.
really confused because you slid down so fast, and I
Sorry.
just saw that. And then,
Sorry. Okay, Lauren?
Would it be negative cosine x plus 1?
Okay, here's right at this step, we reversed it by pulling out that negative. So this became a positive and a negative.
Oh,
Then we just pulled the cosine. I just did it in 2 steps. You could absolutely do it in 1. You could absolutely do it in 1, but your signs should match. All right, algebra tells us either this is 0 or this is 0. And it turns out this negative doesn't really matter, because if we divide both sides by -1, and didn't we just have to do that on the last problem? So the question is, where's cosine x equals 0? Where is it? Pi over 2 and 3 pi over 2. I'm going to start a list down here. And then for the other one, which I'll change colors for, we would add 1 to both sides. Where does cosine of x equal 1? 0 or, yeah, 2 pi. Either way, this one said, I think they don't want us to use the 2 pi. Wasn't that an open bracket up there? Back before example 4? Was it an open bracket on the 2 pi? Okay, so then we'd give them 0. We'd say 0. But this didn't say from 0 to 2 pi. It changed directions. So here's what we need to do. We have to give them all. So let's see if we can give them all. Do you remember what you have to slap on behind it if we want to give them all? N is z, but how do we get it to generate all of the solutions? Exactly. So we will write 0 plus 2 pi n and set of all integers. But that looks kind of, because 0 plus anything is just the anything. So most people would just pretty that up and say 2 pi n is a set of all integers. Then we'd have pi over 2 plus 2 pi n is a set of all integers, and 3 pi over 2 plus 2 pi n is a set of all integers. Unless you noticed,
Can you just do pi over 2 plus pi n?
You could. So that was the next point, and Cy just caught that, and that is, because these are going to be exactly pi units apart, we could just do pi over 2 plus pi n and the set of all integers. But we have decided we're going to take this from everybody too. We don't want you to have to stop and think a lot about simplifying these pieces. So if you don't catch that these are pi units apart, we will absolutely take those 3 answers right there, and that's okay, because we want to know that you understand how to get all the solutions as you do that. All right. Yep. This one over here. These are pi units apart, and here's, Cy, how did you see it? How did you know that they were pi units apart?
Because one's straight up and straight down, so it's just half the circle. It's pi.
So Cy visualized it. Other people will do this. They'll say, well, wait a minute. If I add 1 pi to this, that will give me 3 pi over 2, because 2 pi over 2 plus this is 3 pi over 2. So some people will do it algebraically, and like Cy said, he did the visual. Here's pi over 2, here's 3 pi over 2. Oh, they're just 1 pi apart. Let's do it this way. Absolutely acceptable. Absolutely acceptable. If you want to condense these last 2 to this would be the other set of acceptable answers for that problem right there. So if you notice it and you change it, yeah, we'll give you credit for that. Absolutely. Alrighty. Solve the following equations. This one's not an all. This one is interval from 0 to 2 pi, not including the 2 pi. This gets different. 3x. I don't see any triple angle identities here. So things have changed. What we do know is this. We know that the graph of sine looks like that. And normally, this period is 2 pi. But that's 2 pi over b. That is a 3 with the x. If there's a 3 with the x, is that a compression or a stretch? Yeah. It is a compression. That means this graph is going to cycle 3 times in that 2 pi, because the new period for that would be 2 pi over 3. And I know this is not going to work out right, so let me try and cheat a little bit by making some cheater lines. So we'd have 1 sine, 2 sines, 3 sines. It's not just going to give us 2 answers, it's going to give us 6. So we should be able to find 6 answers. But we should be able to use what we already know. So, well, let's just solve it algebraically and say we'd add 1 and divide by 2. Sine is 1/2. I think we did that one earlier too, didn't we? I mean, if opposite is 1, that's a 30-degree angle. It's positive. So what do we get in radians for that? Pi over 6. What's the other one? 5 pi over 6. Remember, everybody, we did that earlier. We had to come up with the positive signs. And if we wrote the answer, we'd write plus 2 pi n and instead of blah, 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 blah. But here's what we know. This isn't just 1x. This is 3x. Oh. So that's 3x. So if I want to know what angles this is going to be, all I have to do is divide everything by 3. Yeah. That's what happened over here. This 3 in front divided everything by 3. So we could say it's already fractions, let's multiply everything by 1/3. Either way, we're going to get the same answers. This one will lead us to pi over 18 plus 2 pi over 3n. I'm giving you the all solutions again. Got it. So we were done with this one? We need more practice with this. So maybe let's keep going. There's more to this problem. Let's keep going. We do, because we're still slamming those into that 2 pi. Let's keep going. There's another piece that you need to see. We would have to put this in there. But the problem with that right now is we don't know which of our answers are going to put us between 0 and 2 pi. We need to get all 6 answers. And with the formula is the easiest way to get all 6. There's another way, but this is the easiest way to get all 6. So let's divide everything here by 3. Notice how it's not plus 2 pi n anymore? And that's because that period changed. So now, here's what we know. We know that we only want the ones between 0 and 2 pi, but we also know there's supposed to be 6 of them. So this is the easiest way to get them. We have our formula. We're going to put in a 0. We're going to put in a 1. And we're going to put in a 2. And that should give us our solutions. If we put a 0 in for n here, it's going to be pi over 18. So there's the first one. If we put a 1 over here, this is going to be pi over 18 plus, well, it would be 2 pi over 3, but we would want to multiply the top and the bottom by 6 so that we could add those two together. So that's going to give us 13 pi over 18. And let's see if we can get one more out of that. So now if we take 13 pi over 18 and we add another 12 pi over 18, we'll have 25 pi over 18. Are all three of those from 0 to 2 pi? They are. This last one is not going to make it all the way 2 times around. It isn't going to happen. Now if we went one more, let's just say we put a 0, 1, a 0, 1, a 2 in here. If we put a 3 in here, we already know we're going to be over because there's supposed to be 6 solutions. There should be 3 from this one and 3 from this one. But if we put it in, we'll notice, oh, wait a minute, I just went over 2 pi because that would give us 37 pi over 18, and that's too much. So now let's go down to the 5 pi over 18. Let's put a 0 in there. What do we get if we put a 0 in for n? 5 pi over 18. And don't forget, we were using it up here. 2 pi over 3 is the same thing as 12 pi over 18. So what would the next one be? 17 pi over 18. One more. 29 pi over 18. And again, if you tried to go one further, you'd realize, wait a minute, I've gone beyond 2 pi. That is the easiest way to get your solutions, is to just keep going with the formula for a while and then generate those answers out of there. Otherwise, you get the first answer, and then you're continually just adding 2 pi over 3, which is exactly what we did here anyway. So this is the easiest way to get those. There are our 6 answers because it was compressed by a factor of 3. So now, that one right there. Based on what we did on the last one, what do you think we should try here? Subtract the square root of 3? Okay, let's give it a try. Divide by 2? Now, I can't help it. At this point, my mind is going to the visual. This said x over 3. What is that doing to the graph? That's a stretch. So in my mind, I've got this question of, okay, we've got cosine, but what's going to happen if we stretch that out by a factor of 3? Well, let's see. Let's see. So we're at this point, we need the cosine to be negative square root of 3 over 2. Okay, cosine. Cosine is adjacent. So if the adjacent side is the square root of 3, that means the opposite is a 1. Hey, this is 30 degrees again. So if it's got to be a negative cosine, you could start here and say, hey, negative square root of 3 over 2. Yep, that makes sense. Oh, that would be a 1. This is a 30-degree angle. But what's the name of this angle in second quadrant? 5 pi over 6. Is that the only negative square root of 3 over 2 we're going to find? No? In fact, the other one's right here, right? So what would the name of that angle be? 7 pi over 6. Those aren't our answers. Those are the answers for x over 3. So let's write our formulas. Oh, let's squish this in here too much. So this was for x over 3. So how are we going to get x? Multiply everything by 3. Okay, so that would give me x equals 15 pi over 6 plus 6 pi n, and x equals 21 pi over 6 plus 6 pi n. Wait a minute, 15 pi over 6? Isn't that more than once around? Were we supposed to just give answers for once around? How about 21 pi over 6? Is that more than once around? Doesn't mean there aren't any solutions. What it means is there's no solutions on the interval they asked us to do. That 3 stretched this out huge. We can't give them solutions from 0 to 2 pi. So we have to put no solutions in the given interval. It's more than once around. Can't do it. Can't do it. But at least we were able to get to the point where we could tell we couldn't do it. Alrighty, let's look at this one. No quadruple angle identities for us. Let's see, sine of 2x minus sine of 4x equals 0. That we know we're going to have to do. We absolutely know we're going to have to do that. Well, we know stuff about sine of 2x. So if we could change this here's why. It's not a power situation. It's about order of operations here. We would have to figure out the x value times 4 first before we could do the sign, before we could do that piece. Well, we do have some nice formulas for this, don't we? Yeah, we've got a sine of 2u formula there. So we'll get sine of 2x minus 2 sine of 2x cosine of 2x. We had to separate it first. We had to. It's just one of the, it's following the identities of trig rules, you know. And yes, in the end, we are pulling it out, but we have to show that we got it from the identity, not necessarily from just the algebra. Yeah, we can factor it out now that we see we've got the sine of 2x in both of those pieces. But it's like when you're doing the proofs and you have to show every step as you go through there, that's what we have to do here. So let's pull out that sine of 2x. And look at what we have. Just need another set of parentheses there that have that make a lot of sense. Well, zero product property says either this is going to equal 0 or this. Use a different color. It's going to equal 0. So let's take a peek. Sine of 2x equals 0. Sine is 0. So the y coordinate has to be 0. Where's that at? 0 and pi. But this wasn't just looking for sine of x. It was sine of 2x. So let's not forget our little 2x here. And let's not forget what that did to the graph. What did that 2 do to the graph? Compressed it. So we should have more answers, not less. This is a compression. You want to stop and do this one first, or do you want to go over the green? Does that bother you? This one first? Okay. So what are we going to do? Divide everything by 2. Well, 0 divided by 2 is just 0, so we might as well leave that off. Did we have to generate? Did they want to know all the answers from 0 to 2 pi, or did this just say find them? Okay, so we're going to find them from 0 to 2 pi, because way back at the beginning where it said x, for example, it says from 0 to 2 pi. So let's see. Well, if we put a 0 in here, we'll get 0 in the top one. If we put a 1 in, we'll get 1 pi. If we put a 2 in, we'll get 2 pi. We're supposed to use 2 pi? No. Okay, so then we go down to the next one. Well, if we put a 0 in here, we get pi over 2. If we put a 1 in there, we've got pi over 2 plus 1 pi. Think unit circle. Pi over 2, 1 pi. Trying to draw it backwards for everybody out there. If we go one more, are we over? We are. All right, so let's go after the green one. Let's see what we can get over there. What would you do to solve it algebraically? Subtract 1. Divided by -2. Oops, my negative looked like my subtraction there. Yeah, it slid in there. Cosine of 1/2. Okay, so adjacent is a 1. That means opposite is a square root of 3. That makes it a 60-degree angle. Positive. So we need that cosine 60-degree angle in first quadrant. What would that be? $60-degree angle in first quadrant. Pi over 3. But again, that's for 2x. Okay. The only other positive place we've got for cosine is quadrant 4. So name of a 60-degree angle in quadrant 4. What is it? Five pi over 3. Remember, all the way around would be 6 pi over 3. All right, once we have this, what do we do about that nasty little 2? Divide. Makes sense that it's pi n because again the period is 2 pi over 2. Pi n. So let's see what we can get from those. If we put a 0 in the top one, we're going to get a pi over 6. Put a 1 in, what do you get? 7 pi over 6. If we do one more, are we going over? We are. Right, so let's go down to the bottom one. Pretty obviously with a 0 in there, we have 5 pi over 6. What would the next one be? Think of pi as 6 pi over 6, and then it gets a lot, 11 pi over 6. There we go. 8 different solutions for that one. Hey, was that it? Oh, I thought we had another 3. Again, if in your homework it says give all solutions, then you're leaving this stuff in that says pi over 6 plus pi n and the set of all integers. But if it says from 0 to 2 pi, we want to generate them. Either way, it's a good idea to have those formulas. That's the best way to generate those quickly. All right, so you should be able to finish that one. And yeah, because we didn't get done with what we needed on, let me scoot that up a little bit, on Friday, I'm going to give you an extra day or two to finish these up. Because that would be a lot to do in one night. I know, because I did them on Friday night. Come on, behave now. Okay,